Guten Tag and welcome to the second portion of our data models presentation for CIS 3107, Database Modeling. We will be covering the evolution of data models from section 2.5 in our textbook. In this second presentation, we will explore how the major data models evolved as the quest for better data management led to several models that attempted to resolve the previous model's critical shortcomings and to provide solutions to the ever-evolving data management needs. The hierarchical model was developed in the 1960s to manage large amounts of data for complex manufacturing projects, such as the Apollo rocket that landed on the moon in 1969. The model's basic logical structure is represented by an upside-down tree. The hierarchical structure contains levels or segments. A segment is the equivalent of a file system's record type. Within the hierarchy, a higher layer is perceived as the parent of the segment directly beneath it, which is called the child. The hierarchical model depicts a set of one-to-many, one column M, relationships between a parent and its child segments. The network model was created to represent complex data relationships more effectively than the hierarchical model, to improve database performance, and to impose a database standard. In the network model, the user perceives the network database as a collection of records in one-to-many, one column M relationships. However, unlike the hierarchical model, the network model allows a record to have more than one parent. While the network database model is generally not used today, the definitions of standard database concepts that emerged with the network model are still used by modern data models. The schema is the conceptual organization of the entire database as viewed by the database administrator. The subschema defines a portion of the database quote, seen, unquote, by the application programs that actually produce the desired information from the data within the database. Other standard database concepts are data manipulation language, DML, that defines the environment in which data can be managed and is used to work with the data in the database. The schema data definition language, DDL, enables the database administrator to define the schema components. As information needs grew and more sophisticated databases and applications were required, the network model became too cumbersome. The lack of ad hoc query capability put heavy pressure on programmers to generate the code required to produce even the simplest reports. The relational model is based on mathematics set theory and represents data as independent relations. It was first introduced in 1970 by E.F. Codd of IBM. To use an analogy, the relational model produced a, quote, automatic transmission, end quote, database to replace the, quote, standard transmission, end quote, databases that preceded it. Each relation or table is conceptually represented as a two-dimensional structure of intersecting rows and columns. The relations are related to each other through the sharing of common entity characters or value in columns. Each row in a relation is called a tuple. Each column represents an attribute. The relational model also describes a precise set of data manipulation constructions based on advanced mathematical concepts. The Relational Database Management System, RDBMS, performs the same basic functions provided by the hierarchical and network DBMS systems, in addition to a host of other functions that make the relational data model easier to understand and implement as outlined in Unit 1. Arguably, the most important advantage of the RDBMS is its ability to hide the complexities of the relational model from the user. The RDBMS manages all the physical details, while the user sees the relational database as a collection of tables in which data is stored. The user can manipulate and query the data in a way that seems intuitive and logical. In a relational diagram, tables are related to each other through the sharing of a common attribute or value in a column. For example, the customer table in Figure 2.2 might contain a sales agent code that is also contained in the agent table. The common link between the customer and the agent tables enables you to match the customer to his or her agent, even though the customer data is stored in one table and the sales representative data is stored in another table. We will cover this model in much greater detail in Unit 3. Another reason for the relational data model's rise to dominance is its powerful and flexible query language. Most relational database software uses structured query language, SQL, made up of three basic parts: a user interface, a set of tables stored in the database, and the SQL quote engine, end quote. The end user interface allows the user to interact with the data by automatically generating SQL code. The collection of tables are independent from another, while the rows in different tables are related based on common values in common attributes. Largely hidden from the end user, the SQL engine executes all queries or data requests. We will explore SQL or SQL thoroughly in Units 8 through 12 in this course. Because it is easier to examine structures graphically than to describe them in text, Peter Chen introduced the Entity Relationship (ER) model in 1976, which quickly became widely accepted as the standard for data modeling. ER models are normally represented in an Entity Relationship Diagram (ERD), which uses graphical representations to model database components. Usually, when applying the ERD to the relational model, an entity is mapped to a relational table. Each row in the relational table is known as an entity instance or entity occurrence in the ER model. The ER model uses the term connectivity to label the relationship types. The name of the relationship is usually an active or passive verb. Figure 2.3 shows the different types of relationships using three ER notations: the original Chen notation, the crow's foot notation, and the newer class diagram notation, which is part of the Unified Modeling Language, UML. In the figure, entities and relationships are shown in a horizontal format, but they may also be oriented vertically. The entity location and the order in which the entities are represented are immaterial. Just remember to read 1:M relationship from the one side to the M side. The crow's foot notation is the design standard we will use in this course and explore in more detail in our next unit. Increasingly complex real-world problems demonstrated a need for a data model that more closely represented the real world. In the Object-Oriented Data Model, OODM, both data and its relationships are contained in a single structure known as an object, which are an abstraction of a real-world entity. In turn, the OODM is the basis for the Object-Oriented Database Management System, OODBMS. The OODM is said to be a semantic data model because semantic indicates meaning. In this model, attributes describe the properties of an object, and objects contain all the operations that can be performed on it, such as changing its data values. Because objects include data, various types of relationships, and operational procedures, the object becomes self-contained, thus making it, at least potentially, a basic building block for autonomous structures. Objects that share similar characteristics are grouped in classes. A class is a collection of similar objects with shared structures or attributes, and behavior or methods. Classes are organized in a class hierarchy. Class hierarchy resembles an upside-down tree in which each class has only one parent. Inheritance is the ability of an object within the class hierarchy to inherit the attributes and methods of the classes above it. Object-oriented data models are typically depicted using Unified Modeling Language, UML, class diagrams that describe a set of diagrams and symbols you can use to graphically model a system. To illustrate the main concept of the object-oriented data model, consider a simple invoicing problem. In this case, invoices are generated by customers. Each invoice references one or more lines, and each line represents an item purchased by a customer. The object representation for this simple invoicing problem, as well as the equivalent UML class diagram and ER model. The object representation is a simple way to visualize a single object occurrence. Facing the demand to support more complex data representations, the relational model's main vendors evolved the model further and created the Extended Relational Data Model, ERDM. The ERDM adds many of the OO model's features within the inherently simpler relational database structure. The ERDM gave birth to a new generation of relational databases that support OO features that focus on better data management, which is why the DBMS based on the ERDBM is often described as an object/relational database management system, O/RDBMS. With the rise of the Internet data revolution, extensible markup language, XML, emerged to manage unstructured data for the efficient and effective exchange of all data types. The amount of data being collected grows exponentially every year. According to IBM, quote, every day we create 2.5 quintillion bytes of data, so much that 90% of the data in the world today has been created in the last 2 years alone, end quote. Big data refers to a movement to find new and better ways to manage large amounts of web and sensor-generated data and derive business insight from it while simultaneously providing high performance and scalability at a reasonable cost. The basic characteristics of big databases: volume, velocity, and variety, or the 3 V's. Volume refers to the amounts of data being stored. Velocity refers not only to the speed with which data grows, but also the need to process this data quickly in order to generate information and insight. Variety refers to the fact that data being collected comes in multiple different data formats. The problem is that the relational approach does not always match the needs of organizations with big data challenges. It is not always possible to fit unstructured social media and sensor-generated data into the conventional relational structure of rows and columns. There is a hefty price tag for expanding hardware, storage, and software licenses needed for the volume of data, and OLAP tools prove inconsistent in dealing with unstructured data. In order to create value for their previously unused big data stores, companies are using new big data technologies. Hadoop is a Java-based, open-source, high-speed, fault-tolerant distributed storage and computational framework which uses low-cost hardware to create clusters of thousands of computer nodes to store and process data. Hadoop Distributed File System, HDFS, is a highly distributed, fault-tolerant file storage system designed to manage large amounts of data at high speeds. MapReduce is an open-source application program interface, API, that provides fast data analytic services. NoSQL is a large-scale distributed database system that stores structured and unstructured data in efficient ways. NoSQL is not based on the relational model. It supports distributed database architectures and provides high scalability, high availability, and fault tolerance. NoSQL stores data in key value stores and supports the large amounts of sparse data that is geared toward performance rather than transactional consistency. NoSQL stores data in key value stores. The key value data model is based on a structure composed of 2 data elements, a key and a value, in which every key has a corresponding value or set of values. The key value data model is also referred to as the attribute value or associative data model. The evolution of the DBMSs has always been driven by the search for new ways of modeling and managing increasing complex real-world data. In the evolution of data models, some common characteristics have made them widely accepted. A data model must show some degree of conceptual simplicity without compromising the semantic completeness of the database. Representation of the real-world transformations or behavior must be in compliance with the consistency and integrity characteristics required by the intended use of the data model. In the second lecture, we have discussed the hierarchical and network data models were early models that are no longer used, but some of the concepts are found in current data models. The relational model is the current database implementation standard. In the relational model, the end user perceives the data as being stored in tables. Tables are related to each other by means of common values in common attributes. The entity relationship ER model is a popular graphical tool for data modeling that complements the relational model. The ER model allows database designers to visually present different views of the data as seen by database designers, programmers, and end users, and to integrate the data in a common framework. The Object-Oriented Data Model, OODM, uses objects as the basic modeling structure. Like the relational model's entity, an object is described by its factual content. Unlike an entity, however, the object also includes information about the relationships between the facts, as well as relationships with other objects, thus giving its data more meaning. The relational model has adopted many object-oriented OO extensions to become the Extended Relational Data Model, ERDM. Object/Relational Database Management System, O/R DBMS, were developed to implement the ERDM. At this point, The OODM is largely used in specialized engineering and scientific applications, while the ARDM is primarily geared to business application. Emerging big data technologies such as Hadoop and MapReduce and NoSQL provide distributed, fault-tolerant, and cost-efficient support for big data analytics. NoSQL databases are a new generation of databases that do not use the relational model and are geared to support the very specific needs of big data organizations. NoSQL databases offer distributed data stores that provide high scalability, availability, and fault tolerance by sacrificing data consistency and shifting the burden of maintaining relationships and data integrity to the program code. Thank you for watching our Unit 2 Part 2 presentation. The diagrams and content of this lecture were derived from our textbook. For a more detailed treatment of these concepts, please review pages 41 to 57 in your textbook.